Alright. Hello. Today we're going to be solving this difficult kinematics problem. Um, so let's get right into it. So you can tell right away that this is going to be a kinematics problem, just because of the meters per second. I mean, what else can I say? We also see two-dimensional kinematics being displayed here. So, yeah, let's get right into it. So I'm going to just start by talking about the trajectory of the velocity. So if we pretend like this is a boat and we're launching it, it doesn't really matter what the angle is, well, let's say angle of theta, and we are launching it with a initial velocity. I'm not going to place any um, values in. Basically, we're going to have two components of the velocity, which is not m, VO, V naught meaning initial velocity, with a sine theta, and then V naught cosine theta. So basically, we have these two two velocities. So basically, we also should consider that if there's no air resistance taken into account, this V naught cosine theta is basically going to be like the same at every single point. So as they travel through the arc, it's going to be the exact same, not going to be decelerating or accelerating at all. Versus the V naught sine theta is going up and down, but what is also going up and down is gravity. That's going to be pulling it down. So basically at the top of this curve is where it's going to have uh, the like basically no velocity at all, because the gravity is basically going to be keeping it suspended while its velocity is also pushing it up, so it's not moving at all. So anyways, now that we have that all figured out, I'm going to set up two equations. So the distance in the x direction, I'll just call that change in x, and I'm going to be just using the normal kinematic equation, x equals xo plus VOT plus 1 half AT squared. So our change in x, so I'm going to just write this out. So we have an initial position, I'll just say right there. I'm going to say that's href equals 0 and xref equals 0. So basically, we don't have to really include the initial position. The initial velocity, however, is going to be v naught sine theta, and we're multiplying that by t. And because this is in the, oh crap, not v naught sine theta, sorry, this is x direction, so it's going to be v naught cosine theta times t. And so because this is in the x direction, there's no forces acting on it that are going to cause it to accelerate or decelerate, so that's going to be our final equation. Now the change in y is going to be a little bit more complicated. Again, we're starting with a initial position of 0, so we're just going to put a change instead, and we're not going to have x there. So its initial velocity, again, is v naught sine theta. So v naught sine theta times t. And then I'm going to add on the 1 half AT squared. Of course, A is going to be gravity in the negative direction. I'll just put 9.8, actually. This is a negative sign. 9.8. And then we have T squared. So, at this point, you might be thinking, okay, so now we have two equations. What are these even representing? So what we want to do is we want to put a point basically where the change in x and the change in y, we're going to smush them into one equation so we can plug in our x distance and our y distance. So basically we're going to eventually be putting 2500 in for x and 1800 in for y. So one thing that, or basically if you're looking at this, we should know that there's two things that we don't know, which is not v naught, theta and time. So we don't know the angle or the time. But do we really care about the time? So if we're looking at this question does not ask about time, it just asks about the angle. So what I'm going to do is I'm going to solve for time in this equation by dividing everything else by that. So we get a value of time equals the change in x over v naught cosine theta. So now that I have this value for time, I'm going to take that and plug it into this equation, and that'll fulfill our need to have both change in x and change in y. So I'm going to rewrite out this full messy equation. So change in y equals VO sine theta, and then we're multiplying that by change in x over VO cos theta, which is just plugging in t because this equals t. And then we're going to add, I'm going to just say actually minus 4.9, just to make it simpler. I just multiplied 1/2 by negative 9.8. And then we have, again, t squared, which is change in x over v naught sine theta, and that's squared. So right away we should be seeing some things canceling out and some things not canceling out. So one of the things that we might notice cancels out is the v naughts here. So what we can do is we can rewrite this as change in y equals v naught over v naught sine over cosine. Basically the v naughts cancel, so it's going to be like v naught over v naught, which is just 1. And then it's going to be sine theta over cosine theta, which is a trig ID. We can know that equals tan theta. And then all that's left is change in x. So we have change in x tan theta. So I'll just write that out over here, just in case that was confusing. So VO sine theta times change in x over cosine theta VO, so these two cancel. Sine and cosine equal tan. And then we're just multiplying it by change in x. So that's where we get this from. And now the fun part, which is negative 4.9 times, I'm going to just put this as change in x squared over VO squared cosine theta squared. I know a lot of people write cosine squared theta. I really don't like that. I'm going to put cosine theta squared. So now if you're looking at this, you might be like, well, this doesn't really help. We have a tan over here and a cosine theta over here. What are we supposed to do with that? So that brings me to the next thing. The only real reason why this problem is difficult is because of this ID, which they expect you to know for some reason. So basically 1 over cosine squared theta is equal to tan squared theta plus 1. So basically what we can do is we can factor out 1 over cosine squared theta here. So basically I'm going to just take this entire block thing we have here, which is change in x squared over VO squared and cosine squared. So change in x squared over VO squared and then cosine squared. So that's the same as saying change in x squared over VO squared times 1 over cosine squared theta. I wrote it, oops. Okay, and from this ID we know that this equals that. So it's basically equivalent to saying change in x squared over v squared times tan squared theta, and then we still have to add the 1. 1 times all this is just change in x squared over v squared. So now if we take this entire thing and sub it in for the block that we have over here, what we're going to get is a really annoying and weird equation that looks very scary. So I'm going to write it all out here. So change in y equals the change in x times tan theta tan theta, and then we have minus 4.9, and then I'm going to just Let's see. How about I'll distribute this, I guess. I mean, sure. Actually, no, I'm not going to distribute it. I'll wait to plug in values. So we have change in x squared over v squared, and then tan theta squared plus change in x squared over vo squared. Okay, so from here, let's check our givens. So from the thing, we can see that the change in y is going to be 1800 because we're trying to solve for the two angles that'll launch it there. That's the whole goal of this problem. And then we're going to also solve for 2500 meters, and then the v initial, and then we're going to be solving for the angles. And I think that's all we really need. So the change in y equals 1800 meters. Change in x equals 2500, I believe. Let me just double check that. Yep, the initial velocity is 250 meters per second, so VO equals 250 meters per second. So now I think we're ready to solve this. So we are going to get a bunch of annoying numbers, and I'm going to whip out my graphing calculator. So this is 2500 tan theta. Okay, so now the difficult part. So from here, I'm going to just do all this in my calculator. So 2500 to the power of 2 divided by 250 to the power of 2 is equal to 100. Wow, what a nice thing. So we're going to multiply that by 4.9. So 4.9 times 100, sorry, is 490 tan squared theta. And then again, I'm going to just double check this. 2500 power of 2 divided by 250 power of 2. Again, 100. And that's still times 4.9. And then we have minus 490 because that's 4.9 times 100. So now from here, this looks a little bit more manageable. What I'm going to do is I'm going to take this, shove it to the other side by subtracting it. So negative 1800 plus, or minus, I guess, 490 is equal to 2290. So I'm going to just set this up to look like a quadratic equation. 490 tan squared theta, crap, I did it again, whatever. 2500 tan theta, and then we have minus 2290, which we've gotten from saying 1800 and 490 combined. This goes to the other side. So what will this give us? This will give us two angles. So I'm going to plug it into my graphing calculator. And, oh, actually it won't give us two angles, it'll give us two tans. So, yeah, that's another thing to talk about. So basically, when we plug this in, we're getting these as our x values. So just saying that this is x squared and that's x. So basically, the two values we get are going to be in tans of theta. So we're going to have to take the inverse tan or arctan of them. So the two values I get are tan theta equals 1.1966 and tan theta equals 3.905. I'll add a 3 there. Why not? So I'm going to take the tan minus 1, and this will give us two angles. And so we have theta, equals 50.1 degrees, and then theta also equals 75.6 degrees. So now if we look back at the equation, we can see that we're nowhere close to being done. Unfortunate. So we figured out what these two angles are. So now what we're going to be seeing is how far these two things are shooting to see what the safe range for this little ship is going to be. So to do that, we're basically going to have to figure out what the maximum distance is. So we're going to start doing that by basically going back to our original equations over here of y and x. So I'm going to set an equation and say the maximum height. So the maximum height is going to be where the initial velocity is going to be whatever our initial velocity is in the y direction. So that's just going to be VO sine theta. And then our final height, or final velocity, is going to be 0, because basically at the top of the curve, the velocity is equal to 0 in the y direction, because gravity is equivalent to the acceleration of the thing. So basically it's not moving at all, or it's just pulling it down to come back down. I don't know. Basically the final velocity is going to be 0, and we know the acceleration is going to be negative 9.8. And so we're going to solve for, how about, we can solve for the time, I think. So we get our kinematic equation, we get V equals VO plus AT. So I'm going to solve for time just to have it here. And we know our velocity initial is going to be VO sine theta, and our velocity final is going to be 0. So that means, and acceleration, of course, is negative 9.8, or just gravity. So we have t equals VO over 9.8. This is sine theta. We have VO sine theta over 9.8. So that's the time it takes to reach that point. But we want a overall like height. And honestly, at this point, we have the time it takes to go half of the way. So what we can do is we can just finish that off and put it the entire way. So I'm going to switch around a little bit and solve now for the distance of the x portion. So I'm going to recycle this equation again. And instead of time, what I'm going to be doing is I'm going to be, or I'm sorry, this equation. I'm going to be putting in what we calculated for time. So the change in x, or we can call this x half, because basically the time it reaches the top is going to be halfway through the arc, assuming a fully normal whatever arc, is going to be v cosine theta, and then times t, which we said was VO sine theta over g. So we can multiply VO by VO, and so we get x half equals V naught squared, and then we have cosine times sine theta, and then over g. So we want the entire distance, so this is giving us half. We want the full distance, which is another x. So we're going to just multiply this by 2 and say x max this time, which is the maximum distance it can travel in the x direction, is equal to, I'm going to shove a 2 in here. So VO squared times 2, I'll just put sine, cosine over g. Trig identity, 2 sine theta cosine theta is equivalent to sine 2 theta, so we get x max is equal to VO squared sine 2 theta over g. So you might be like, why did you just do all that? Why do you waste 5 minutes of my time? Basically, I want to find, this is giving us the equation for the maximum distance that these two things are going to be shooting. So now we're almost done. We have our two angles, and we have an equation that'll tell us what the maximum distance that they can fire is. So I'm going to take these two values, 50.1, 75.6, plug them into here. So we're going to get x1 and x2. So I'll start with the first one. Velocity initial is 250 squared times sine. And then the first one was 50.1. It's 50.1 divided by 9.8. So we have a x1 distance, the 50 degrees, of 6276 meters. 75.6 degrees now. 250 power of 2 times sine 2 times 75.6 divided by 9.8. And we have x2 equals 37.2 meters. So if we look back at this drawing, basically one is going to be 3072 meters, which is like roughly over here, and then the other one's going to be way out here at 6,000 meters. So it's saying, what are the distances from the western shore, which is 300 meters out, or 2,800 total meters out, that we are safe from the enemy ship's bombardment. So we have these two values, and we want to be 2,800 meters out. So we're going to take this number and subtract from there. So the distances are going to be basically not at these 2 points. So 3072 minus 2800 is 272 meters. 2 meters. So you don't want to be there. And you also don't want to be at 6276 minus 2800, which is 3476 meters. So these two distances are the two distances where you don't want to be at, because basically, if we have our cliff here, and the boat's here, it's 2500, and then the cliff is like 300 from there. So basically, we're going to be like shooting stuff over here. It's going to go directly over that point. So at 273 meters out here, you'll get hit, that'll explode, and also then 3,000 meters away from this point, that's also going to explode, so you don't want your ship there. So anywhere here, here, or outside of here is going to be safe. But you probably don't want to be in between these two angles, because I think you might get something. So let's just say less than that and greater than that. So yeah, that's going to be it. Thank you for watching if you actually watch this. So yeah.